500. Just actually for lesson number 7, I used to introduce logistic regression here, but in redesigning the course, I've decided to move into assumptions and diagnostics, and I used to cover this in 6500, but I think this is a more appropriate place to introduce it. I hate the fact that I'm not going to introduce to you logistic regression. It'll hold off until 6500. But those of you who take 6610 and 6620 get introduced to logistic regression there. So anyway, sorry to be so windy, but that's the justification, okay? All right, let's pump the brakes a little bit. What we've done so far is we've looked at a theoretical nature of simple linear regression and multiple regression. We've looked at setting up our queue, which is using the least squares technique. We minimize this to find our estimates. We've looked at the maximum likelihood estimation process, where we set our likelihood function, take the natural log, take the derivative, set to 0, and solve. And we've seen some pretty straightforward approaches to it, calculating the estimates of beta 0 and beta 1. For example, we all know that beta 0 can be, if we have the estimate for beta 1, that we can estimate beta 0 this way. We've seen a couple of different ways to estimate beta 1 straight up. We can take this SXY, the ratio of SXY over SXX as defined in a previous video. And there's another one, probably one of the more common ways that we can, no subscripts, but we know running from I equal 1 to n, that we can, from this evolves from solving the normal equations, and it's a very handy way to calculate the estimate for beta 0. Now, once we've done, okay, let's pump the brakes. But again, theoretical basis here for simple linear regression and multiple regression. But for the most part, if we want these values, we're going to use some technology. In this class, we use R. Now, some people may question using a statistical package. I don't know of a master's or doctoral level program in statistics that doesn't require learning a statistical language, a programming language. Usually that's SAS or even SPSS if you want something that's Windows driven. But SAS is expensive, right? R is free, so let's just say what it is. I like R. I mean, it works. So we've gone with it. Now, once we use R to create our model, the first thing we're going to look at is whether the individual predictors are significant, and we'll do this with the t-test, and I'll show you how we report those results. The next thing we would want to look at is the model significant? And what we'll do here is we look at the f-test. I'll show you how to report that in this video. The next thing we get into is the model useful? And what we typically do there is we look at R squared, or if we have multiple regression, because again, there's this phenomena that the more predictors that we add to our model, the R squared will just naturally increase. Well, we don't want something that's artificially increased just because of the number of predictors. So this adjusted R squared supposedly controls for the inflated. Now, moving into number 5, does the model fit the data well, and are the assumptions met? So this is going to be the focus of lesson number 7. Once we've run everything, have we checked all the boxes for the assumptions? and does the model fit the data well? Now, if I'm teaching ANOVA, just straightforward ANOVA, where we compare means for more than two groups, and we'll do this in 6610, we check our assumptions before we run the model. But with a linear regression, in the linear regression case, it's kind of strange that we have to run our model first and then check our assumptions. And the reason being is because the errors play a really important role in the model diagnostics. Now, let's state the assumptions. So assumptions for our simple linear regression and our multiple regression models. Now, the first one is that our y values, and this is equivalent to saying also that our errors are independent. Now, turns out that there's no plot that we can necessarily look at that gives us the answer to the independence assumption for the y values and the errors. This is more of a study design issue. Now, just let me give you an issue of, a situation where we might have a concern with independence. Let's say, for example, that we're wanting to examine the relationship between, I don't know, two quantitative variables. And we collect our data from hospital number one, right? And our goal is to just be able, so we go in and we collect a sample from hospital number one. And all we want to do is we want to be able to generalize to hospital number one. Well, we really don't have a problem with independence unless there's some sort of internal wackiness going on with the data collection. But let's say that we also collect data from hospital 2 and collect from maybe hospital 3. And instead of generalizing just to these three hospitals, we want to generalize to all hospitals. So what we have here is we have nested data. And what we know from schools and hospitals and all kinds of different nested designs is that these values tend to be related. These values tend to be related. These values tend to be related. The fact of the matter is some hospitals are just better than others. Some hospitals have different characteristics for patients. Arguably some hospitals in the Appalachian region have higher rates of diabetes and higher rates of heart disease than maybe a hospital that is in a maybe an area where people are just more highly educated and just take better care of themselves. And there is studies out there to show that there's a relationship between the two. So if I'm trying to put all these together where there's actually in a nested effect, a nested design, where these inner samples are related, then I get into an independence assumption. Could be violated. But what I want you to know at this point, well, I want you to know that, but I also want you to know that there's no plot that we spit out that just addresses independence. Well, not true for number 2, 3, and 4. Number 2, 3, and 4, we actually do look at plots and errors and distribution of errors and different things. All right, so the first thing we want is we want that the y values, actually the second thing we want, this is the first thing we want, but the first thing we want where we actually conduct a diagnostic, in this case using R, is that our y values can be expressed as a linear function of the x values. Now you got to be really careful with this one. R will let you put in anything. It'll let you put in any x and put in any y, and if you do the LM function, it will create a linear function between the two. Doesn't mean it's appropriate. We have to investigate these things. The next thing that we need to look at is the variation of the observations around the regression model. Is constant. And we give this a fancy name. It's called heteroskedasticity. No, I got that wrong. This is called homoskedasticity. Can't see, people. Let me get over here where I can see this. If you could see the way I create my videos, I'm actually about 2 feet from this. My eyes are far too much information. So anyway, so I have to get over there, and the lighting's not real great over here anyway. So homoskedasticity is the that we have equal variation, or constant variation around our regression model. The fourth one, for any specified x value, the y values or our errors are normally distributed. Now, I want to run through a couple of examples, and a couple of plots that we're going to use. And I'll tell you what, let me just go ahead. One of the plots that we're going to use, well, we're going to use quite a few plots, but there are 2 plots that I want to talk about, and I've talked about these before. One plot, we look at our fitted values as our x, and then we look at our residuals, which we know are just our errors, on the as our dependent variable, and our fitted are the independent variable. Well, we want to look at this because we want to look at the equal variance assumption. And if this equal variance assumption is satisfied, we're going to get just a shotgun blast, as I've talked about before. So it looks like a random, no discernible patterns. When we check our the normality of our errors, we actually look at the standardized residuals over the theoretical residuals. I feel like I have something crawling on my head. It's got me distracted. Seems like I always get distracted by something. And what we can look at is we can look at the y equal x line, and we expect these observations to fall fairly closely. Yeah, I don't know what's going on. I feel like I got something crawling on my head, and I don't like it. So these lines, these points should fall very close to that vertical line. Now, a couple of examples. I tell you what, let's get out of here and go to R. And on R, I actually have a data set. It's just called X and Y, and this is nothing. This is not real life data. These are data sets that I actually created. So to make a point. So a couple of models going here. First of all, I want to use X1 to predict Y1, and then another model I want to use X2 to predict Y2. and just show you a couple things that we run into, and how sometimes we actually do an eyeball test, and the eyeball test doesn't necessarily always work. So I don't know if that is as yeah, sorry. I don't know if those sounds are as loud to you as they are me, but it's just like it like shatters my teeth almost when I get an email. All right, where are we? Okay. One thing I want to do is let's just first of all, let's say that the goal is to examine the relationship between x1 and y1, and to furthermore explore if a linear model is appropriate for describing the relationship between x1 and y1. All right. So the very first thing I would do is I would just look at the correlation between x1 and y1. And the correlation is 0.99, right? What does that tell us? Well, that tells us the correlation is 0.99. Nothing about examining the relationship between x1 and y1, just exploring if the linear model is appropriate. Doesn't tell us any of that. Just tells me I have a high correlation between x1 and y1. Next thing I'd probably want to do is I'd probably want to just look at a plot between x1 and y1. And I eyeball this one, and I think most people would say that falls nicely on a linear model, doesn't it? So I would think that a linear model would be appropriate for describing the relationship between x and y. Well, next thing I want to do is I want to create my first model, and I'll just call it model 1 because it's between x and y. So I have y1 as a predictor of x1, and I'll do the whole summary model 1, as we all know that we can do, right? And again, I always have tunnel vision. I go to my predictor or predictors. I look at this line, and I see that I have statistical significance. Now, how would I report that? To report appropriately, I would put a t, because this is being the statistical significance of this predictor is using the t-test or a t-distribution. In parentheses, I'll put my degrees of freedom. Well, my degrees of freedom, I don't know what my degrees of freedom are because I don't know my sample size. Well, my sample size must be 10 because I have n minus 2. So, okay, so I can get my degrees of freedom. Next, I need my t-value. So in this case, it's going to be 20.86. And then I am going to either report my p-value if it's above 0.05, or if it's below 0.05, I'm going to report it according to the highest, well, actually the lowest level of statistical significance that we reach. Now, that's a little confusing. So let me grab back over here and let me explain this a little more. So if I have a p-value, again, 0.05 is the first line in the sand that I consider. So if I have a p-value of 0.32, then I just report easy for you to say. I report it as 0.32. Now, when I have a p-value below 0.05, that's when I start to compartmentalize the way I report it. If I have a p-value between 0.01 and 0.05, so 0.032, for example, then I would report this as p less than 0.05. If I have a p-value between 0.001 and 0.01, for example 0.0052, then I'm going to report this as p less than 0.01. If I have a p-value below 0.001, which could be something like, 2.93 e to the negative -0.08, I wonder where I came up with that, right? Again, go back over to our output. Then I'm going to report this as p less than 0.001. Great thing about R is it tells you this in the output. Notice how when I go to my p-value for x1, I have 3 stars. And 3 stars stands for what? Well, it stands for less than 0.001. 2 stars less than 0.01, and 1 star is less than 0.05. Notice for the intercept, we have 0.00194. Barely squeaks in there, right? Bigger than 0.001. So it's between 0.001 and 0.01. So therefore it has 2 stars, and we would report this as p less than 0.01. So for our predictor, x1 in this case, we would report as this. All right, so the next thing I'd probably want to do is I'd want to take a look at the ANOVA of our model 1. And in a simple linear regression case, it's really nice because we just have one predictor, so we don't have any of that goofiness, wackiness to worry about. So to report our model appropriately, we use the F distribution. We have 2 degrees of freedom. Our test statistic is our F values, so 435.1. And our p-value is what? Well, it's 3 places. So again, 3 indicates that we are statistically significant at the 0.001 level. Something kind of cool to note too. Remember the relationship between the mean square error and the residual standard error? Does anybody remember that? Well, if we take the square root of the 2.15, we'll see something very familiar, namely the 1.467 on 8 degrees of freedom. So again, that's one of those things that needs to be tattooed to the brain. Now, again, if I was looking at my assumptions and diagnostics for a straight ANOVA, not ANOVA for regression, but an ANOVA that tests the equality of group means, again, will be taught in 6610, then I test my assumptions before I look at my model, but not so in regression. In regression, I run my model and then use it to test the diagnostics. So now let's take a look at plot, just revisit this. So I can plot my line, and it really has a feel of a linear model, doesn't it? But I start to get some concerns because I notice from my lower numbers that both of my observations are above the line. I notice for my upper numbers that both of my observations are above the line, and everywhere else my observations, my observed y's, are actually below my line of regression. So because of that, when I first eyeballed this thing, it looked like a linear model, hands down, no questions asked. But when I start digging into this more deeply, I'm starting to get a little bit concerned. Now, let's dive into to some diagnostics. R has a really cool feature where if we'll just do plot of our model, it's going to give us four outputs. And it it's a little goofy the way it works, but or at least the way it works on my end. Uh, so hit return to see the next plot. Now the next plot that we're going to see is going to look at our fitted values on the value, our fitted values on the horizontal axis, and our residuals on the vertical axis. This gives us an indication of equal variance. This is before when I told you the plot. Let me show it to you. This is that plot. So when I look at that plot here, then I know we have problems with our equal variance of our errors. So red flag number one. Hit enter again. We're going to get our QQ plot. Now again, we want these points to lie on that line, right? And they don't. So, immediately have another problem with meeting our assumptions. I don't think we can assume that our errors are normally distributed. There's another plot here. This is another assumption, equal variance assumption plot that we can look at. If we again, I don't know if that's loud for you all, but it's really loud for me. If we have equal variance across our fitted values, then this red line should be a straight line. This tells me that my residuals are higher, and then they're lower, and then they're higher over here on the upper end. Well, we knew that kind of from the scatter plot. Just kind of by eyeballing it. And then the final one, we get into leverage. I'll teach that later on. This just has to do with non-constant variance and nonlinearity, so we'll get into that a little later. So when I first started out, and I looked at just the plot of x1, y1, I'm like, well, hands down, heck yeah, that's a linear model is appropriate for describing that relationship. But as I dive into my diagnostics a little deeper, I have some huge concerns that the linear model is actually appropriate. Now, you might say, well, okay, Dr. Darbo, just pump the brakes, Small sample size, agreed. Even more, you made this data set up to make a point. Also agreed. I did. Now let's dive into our relationship between x2 and y2. Okay, hands down, whether you're in a grad level course or even just an introductory statistics course for liberal arts majors, you can see that a linear model does not appear to be appropriate to describe that relationship. I'm going to create model 2. Whatever. I can take a look at this if I want. You can see we have statistical significance at the 0.001 level. We have statistical significance for the intercept at the 0.05 level. Correlation between x2 and y2 is 0.92, which again indicates that if we get sloppy, it indicates to us, falsely in this case, but it indicates to us if we get sloppy that there is that a linear model is appropriate for describing the relationship between x and y. We need to pump the brakes on that one. So let's just do plot 2, plot between x2, y2, and then let's add for our model 2, right? And we can see we have, again, major issues here. We don't want to see patterns. And what I see is from about 3 up until about 8, all of our observed values are below the line. All of the observed values below 2 and above 8 are above the line. So we got some patterns going on here with the variances, or I'm sorry, with the errors that are extremely concerning to me. So I want to do plot model 2 and get into some diagnostics. All right, we should see a red line, right? We should see a straight red line if we have equal equal variance of our errors. We don't have that. But again, the reason I chose these two plots to contrast is I think it's clear when we ran the scatter plot for y2 over x2 that a linear model wasn't appropriate. Yet the residuals versus the fitted for this are pretty much the same as they were for the first plot between x1 and y1, which did appear that a linear model was appropriate. Daggone it. Okay, so we get in the QQ plot. Again, looks like to me we have an issue with the normality assumption. Again, that red line, if we have equal variances, then that red line should be straight. It's not. Again, it looks like that the errors are larger for the lower and upper values and somewhat the same for the values in the middle. And then we get into leverage, and again, don't know much about that yet, Cook's distance, but we'll learn about that. All right, gang, I think that's all I have. So anyway, the purpose of this video was just to give you a model that appeared to be appropriate for describing the relationship between two variables when it wasn't. There we go again. And getting a lot of emails this morning for some reason. And then, again, the model 2 between x2 y2, it was clear that the linear model was not appropriate. Doesn't mean when we throw the baby out the bathwater and say, well, we can't do the problem. Well, we can do the problem. We just can't describe the relationship between these two variables, x1 and y1, and separately x2 and y2 using linear models. So we'd have to either dive into a transformation or use a different type of model, maybe a quadratic model, for example. All right, gang, all I got. Take care.